This is our second lecture on the properties of functions that we're interested in, which is one-to-one, onto, and bijective. Okay, so here we're looking at a fifth example of a function. Let P be the set of students I had in this Math 6055 class. This looks like 3 years ago. Define a function from the set of students to the real numbers by, now this is a clause thing, so this is like it's kind of writing down kind of an if statement. So let's presume you would have met some if loops, for example. So if P, I'm just going to write SQT, then the Q is equal to the score, else Q equal to 0, end if. So that's just what this this brackets notation means. Okay, we might see it in various different places. So if the student sat the test, it's theirs now. So this quick test was just a little paper test I gave on the first day to get an idea of where people were at. So you either get that score or else write 0. Now, if we don't have the otherwise clause, Q is not a function. And the question is, why is it not a function? Well, the set of inputs is the set of students. So every single input has to have an output. So you can't just say, oh, there's no output. You have to give it some output. And here we choose to give it 0. So the scores ranked from top to bottom look something like this. And if we call by PI, the person who got the highest score, what do the ordered pairs look like? So Q, so the first person, say P1 person, that's the input, the output is their score 22. Second person, P2, output 21, because the input is the person, the output is their score. Third person, output 18.5, and the fourth person, output 18.5, ... and then there's lots of people, so there was probably 40 in the class, so certainly the last person, not everyone sat the test, so some people at the end scored 0. So this is what the ordered pairs look like, and the question is this one-to-one, is this onto, is it bijective? So we'll answer it kind of twice. We'll do it without a picture and with a picture. So one-to-one says that every output appears in only one ordered pair, but here you have 18.5 appearing in 2, so it's not one-to-one. Now we will draw a picture of this below because we're going to try and push the arrow diagram picture. And onto is everything in the codomain is it. Now the codomain is the real numbers. So like there's no negative numbers here, so it's definitely not onto. It's very, very far from onto. But I think easier than that, we could just go to 21.5 or even 20. Nothing hits 20. So 20 is not hit. So it's not one-to-one, or excuse me, not onto. And actually, as soon as we said it was not one-to-one, we could have said it's not bijective. So this implies that Q is not bijective. Okay, let's draw a picture of some of this. So the input is the students in the class. The output is the real numbers. You actually, if I wanted, I could actually nearly draw a number line. Well, will I do that? It's a bit different, but maybe it's confusing things. I'll draw it. Maybe I'll draw another one over here. But it's not. It's kind of not. It's quite alternative to do that. So we're inputs. So the domain is P, the set of pupils, students. We'll say there was 40 in there, and the codomain is the real numbers. So we're talking P1, P2, P3, P4, ... down to P40. And in terms of the outputs, we'll just look at just these ones. So now obviously you can't write all the real numbers here. That's why actually a real number line would be a little bit better. 18.5, 18.5. Oh, sorry, you don't write them twice, and say 0. And I think I want to get 20 in there as well. Okay, and then the function is Q. So P1 scored 22, P2 scored 21, P3 scored 18.5, and P4 also scored 18.5, P40 scored 0, and others as well, and nobody scored 20. So it's not 1-to-1 because of that. Two things hit 18.5, and it's not onto because nothing hits 20. So not 1-to-1, not onto. So the alternative here would be that if you want to look, it's I probably shouldn't even do it, but you could draw a real number line. And you could kind of draw it like this. So you got like 22, 21, 20, 19, 18. And just in terms of what we've seen over here, so P1 gets sent here. 22, 21, 20, 18. P2 gets sent to 21. Two things get sent to 18.5. And a few things will get sent to 0. You can see it's highly not onto. Loads of things aren't hit. Every single number between 22 and 21 is not hit, because remember the real numbers is everything on the real number line. Okay, that's that. Here we have the graph of a relation. Now I'm going to probably write this as the coordinate graph. Now remember what you do to coordinate graph. You write you take the ordered pairs, so the relation is a set of ordered pairs. Now here, because it's a relation on OR, and actually OR is what's called not countable, you can't list all the ordered pairs. Now we'll chuck some of them in here. So for example, 0 is related to 3, -1 is related to 0. I don't think there's, there's more and more and more. And if you, so there's infinitely many, like there's a real, there'll be something for pi. It's just a relation. I have no notation for this now. So we'll just put it in roughly something like, let's say 1.91, and suppose it goes on forever and ever. So anyway, and this goes on forever and ever and ever, but you can't even list them. So it's a relation because it's a set of ordered pairs. The first thing is a real number, the second thing is a real number. And so if you graph all of them, which you can't really do manually, you have to, it exists as a mathematical object, but you have to use software to approximately draw the graph. Well, graph all the coordinates. You have the coordinate graph of a relation. So the question is here, is it a function? Is it 1-to-1? Is it onto? And is it bijective? Now there's one thing, it says it's a relation on R, but we don't have any information. We only have information around here. And what we're going to do whenever a question like this is given, we're just going to assume that nothing weird happens outside here. I mean, you can't guarantee that this goes bonkers over here, but we'll just assume that everything outside this part of the graph is fine. Okay, so first of all, is it the graph of a function? And to tell if something is a function, use the vertical line test. If every vertical line hits the graph once and only once, then it's a function. And the answer is yes. Is it the graph of a function? So the first question, yes, by the vertical line test. Every vertical line hits the graph exactly once. Second thing, is it 1-to-1? So what we do now is we use the horizontal line test. So the issue here is if we look at, say, 0, 3, and if we draw this, we can see that there's actually this horizontal line, which is y equal to 3, cuts the graph once, twice, 3 times. And that means that if you look at the coordinates, so this one, let's say, is something, we'll just do it roughly. This is like 2.43, roughly, and this is roughly maybe 4.93. And so if we kind of included those in the ordered pairs, or even if we drew an arrow diagram now, well, let's, okay, so we got 0, 3, We also seem to have 2.43 roughly, and we have 4.93 roughly, so they should be in there as well. We see that the output tree appears more than once. It appears 3 times, so it's not 1-to-1. We can draw it with an arrow diagram. Now, it's probably good that we said it's a function first. If it's not a function, you can still do the arrow diagram, but if it's not a function, you're not really going to analyze it in terms of being 1-to-1 or onto. You don't really talk about, if it's not a function, it would just be a relation. You wouldn't talk about a relation being 1-to-1 or onto. Real numbers. I could have again drawn the number lines. I might do that up here just to home in on it. So we've got 3 different outputs, 0, 2.4, and 4.9, all being sent to 3. And therefore it's not 1-to-1. And we're going to write that down here as our answer. So we'll just do the other picture. It's where you instead of drawing these kind of blobs, you can represent the domain as it is, which is real numbers. So real numbers. Oh, the one thing I'm missing is, well, we've no name for the function, so we won't name it. So 0, 2.4, 4.9, all sent to 3. So it's not 1-to-1. Okay, so down here, is it 1-to-1? No, by horizontal line test. And probably it's good to draw the line. Now it's probably difficult. You can't draw all the vertical lines, but just just state it is. And then is it onto? Now actually we can answer the bijective bit now, because as soon as it's not 1-to-1, we can say that it's not bijective, because it has to be 1-to-1 and onto. So this implies not bijective. And finally, is it onto? Well, as far as we can see, it is, because every single horizontal line hits the graph. Now you might say, oh, it doesn't down here, but as I said, we won't think of that. Every horizontal line hits the graph. That means that all of these numbers, certainly that we can see, there is a 4. So like if you pick 8, there's a point here, whatever it might be, 5.58. That means 5.5 is sent to 8, so 8 is hit. So everything is hit. So yes, by the horizontal line test. And then we can ask you questions down here, which we've answered some of these already. It's about understanding in the coordinate graph that the points are input, output. So what does the graph suggest is the value f of 0. So what's 0 sent to? And what does it suggest is the value of 3 at 3. So 0 is sent to 3. So that one's easy. And how about 3? Well, if we go up, looks like 2, doesn't it? Now it's only suggest, because you can't be 100% sure here. So what I'm saying is we got a point here, 3 along the x, 2 along the y, and remember the coordinate graphs, input, output, 3 in, 2 out. 3 in, 2 out. For what values of x is f of x equal to 0? So remember, the f of x is the y coordinates. So where's the y coordinate equal to 0? So if we draw across from where's the y coordinate 0, it's along here. We see the point here, -1. So so basically x equal to -1 is set to 0. And these are what are called, this is the root of f. So the root of a function is a value, an input that produces the output 0. And finally, what does the graph suggest are the values of x such that fx equal to 4? Well, we should find all the points where the, again, f of x is the y coordinate, where the y coordinate is 4. So if we go across here, we seem to get 2 points. This one looks like 1, 4, and this one looks like 5, 4. 5, 4, 1, 4. So f of 1 is equal to 4, and f of 5 is equal to 4. Okay. So this is stuff about the relationship between the properties of function in terms of one-to-one and onto, and the coordinate graph, where you can analyze it using the vertical line test to tell it a function and the horizontal line tests to tell whether it's one-to-one or onto. I better probably just write here. This is about being one-to-one, and this is about being onto. Okay. Right, and we have another question here. So let P be the set of students in this class, so that's comp 1C, and define a function ID from the set of students in this class to n the set of student numbers. So we're going to say, so take a student, let P be in comp 1C, and the ID of student P is equal to the student number. For example, something, whatever it is, or 0, 0, 2, 0, 1, 2, 3, 4, something like that. I think there's 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Okay. Now, what you can actually do here is we can do a little bit of Cartesian products to properly say, like, where do these student numbers live? And what we can do is we can associate a student number with an ordered tuple. So the first thing is OR, and then you get 0. So it's like an ordered pair, except it's not a pair or even a triple or a quadruple. It's got 8 elements, or 0, 0, 2, 0, 1, 2, 3, 4. And this is an element of this set. So it's a Cartesian product. The first thing is in the set OR. Now there's only one option, it has to be OR. And then the second thing is d to the 8. Now d to the 8 is the Cartesian product of d 8 times. So that means all possible lists of 8 numbers where the order matters. So it's an OR together with 8 numbers where the order matters. And that's exactly the case with a student number. The order matters. Okay, so that's kind of saying what the set of student numbers you can model it by as well. This question is ID one-to-one? Now it's certainly one-to-one. You don't want it to be 2 different students. So we'll just draw a little picture for this one. So imagine if you had 2 students, we'll call them student 1 and student 2, who have the same student number. So I'll say it's student number n. So like, say for example something like this. You do not want 2 students, say P1 and P2, to have the same student number. Wouldn't that be absolutely daft? So you can see obviously in terms of computing where the property of being one-to-one is important. Because if you know, it's about identifying something uniquely really by a number or whatever. So it's associating one object with say an ID number. That is a function that has to be one-to-one, because otherwise you look at a student number and that doesn't identify the student. So this is not happening. So is it one-to-one? It has to be one-to-one. If it's not one-to-one, there's a mistake made by CIT. And therefore, okay, that's okay. Is it onto? Now, technically it might be onto, but I'm fairly sure that the student numbers look something like this, and at the moment I think the first 2 numbers here are 0. So for example, if we look at, say, or 1, 2, and then whatever you want after that, 3, 4, 5, 6, 7, 8, there's nobody with this student number. So this is not hit. Now you could set it up differently, where n is the set of student numbers that have been assigned, and then it would be onto, because every single student number that is assigned is hit by the ID function. But I'm setting it up so that the set of possible student numbers, I think this is the place where it naturally lives, they're not all hit, and therefore it's not bijective, not onto, and not bijective. Now we're going to see a little bit later this scenario where you can change the codomain if you have a one-to-one function, and then you can make it what's called invertible on its range. We'll see that a little bit later. Okay, so define a function I from the natural numbers, now this is now where you need to be, you do in this chapter need to know those number sets. I think this is the very first thing we actually looked at. From the natural numbers to real numbers, this is the counting numbers 1, 2, 3, 4, 5, etc. And this is all the real numbers, all positive, negative, decimals, everything. By a natural number sent to itself. It's not onto because a half is not in the range. So like you're putting in natural numbers, can you get out a half? You can't. Maybe if I draw this, it'll make a little bit more sense. I actually think I can draw it as a coordinate graph. Yeah, I can draw it as a coordinate graph. So we put the codomain here, which is the real numbers, that's everything. And let me just do, so this should actually explain what I'm doing. And this is just going to be the natural numbers. And remember the natural numbers, now you can include 0 if you want, it doesn't really change things. 1, 2, 3, 4, 5, 6, 7. And these are the only things in the domain. Well, 8, 9, 10, etc. And now if we, but the thing is here, everything, all of these numbers are in the codomain. So now I'll try and fit 1 to 7 here. So 1, 2, 3, 4, 5, 6, 7. And so the graph should be input, output. So the only inputs are 1, 2, 3. So input 1, out 1. That's the point in the graph. Input 2, output 2. Input 3, output 3. Input 4, output 4. Input 5, output 5. Input 6, output 6. Input 7, output 7. Those of you who know your maths, notice this will be on a straight line because it's kind of like it's like 1x plus 0. Now you don't fill in the lines here because every point on the coordinate graph is of the form input output, and if I join these up, if I did that and I look at say 3.5, certainly here would be 3.5, that's certainly the coordinate here, but 3.5 is not a natural number, so that is not actually in the graph. Okay, and now we can see here it's actually easy enough to answer the questions, is it onto? And if you look at, for example, a half, you can see that nothing hits a half. And a half is in the codomain. So it's not onto because a half is not hit. Is it 1 to 1? Well, by the horizontal line test here, you'd have to say it is. Because if you draw any horizontal line, it hits it. It can't hit it more than once. Okay, so by horizontal line test, is 1 to 1. The other thing is like there's no there's no possible two different inputs that hit the same thing because the inputs are equal to the outputs. And so if you have two different inputs, you have two different outputs. So it's like that 2 to 2 we were talking about in the last lecture. Is it bijective? Well, no, because it's not onto. Bijective, not onto implies not bijective. What if we change the codomain? So this is just kind of sneakiness from R to N to get a new function from N to N. Is this onto? Yes. If you take any number in here, say 473, it'll be hit by 473. Is it 1 to 1? Yeah, basically for the same reason. Like you can't have two different numbers because every number is just sent to itself. Like if you have two different natural numbers, and remember, look what this function does. It just sends the input to the same number. If you have two different numbers here, you can't have them hitting the same thing. Well, why? Well, we can't really use algebra, but this is just not possible. So two different numbers here. This is sent to itself. This is sent to itself. If they're different here, they're going to be different over here. This is not possible. And what that means is it's onto, everything is hit. It's 1 to 1, and so it is bijective. If you're one-to-one and onto, you are bijective. Okay, let's look at another example. Consider the function given by s of x equal to x squared. Is it onto, is it bijective? Now we will study this one a little bit more later in chapter 5, but I think what we're going to do is we're going to give one that we kind of an explainer for now, and then one where we use a bit more knowledge from later on. So the one that we know now is I'm pretty much just going to give you the answer. So real numbers to real numbers, and what I'm going to do is I'm going to partition this up into the positive, and it would be probably, yeah, this will be the positive bits, so I might call that R plus, and the negative bits, and we'll just put 0 there. Okay. So let's put the number 1 here because that's all I'm going to need, and let's put the number -1 here. That's all I'm going to need, and all I'm going to need here is say 1, 0, -1. Okay, so let's just draw some of these. So what's 1 squared is 1. What's 0 squared is 0. Obviously you can't represent everything. And look at -1. -1 squared, -1 by -1 is +1. So we can see straight away that it's not 1-to-1. S is not 1-to-1 because two different numbers hit 1. And, well, look at the other thing. If you take any number, real number, and square it, you get something positive. So nothing in here gets hit. So nothing in here, so for example, -1 is not hit. So that implies that this function is not onto. And as soon as we said it was not 1-to-1, we could have said it's not bijective. So the issue, we might have said, oh, it doesn't hit the negative numbers. So what you could do is, let's just work with the positive numbers. Oh, I was going to draw a different picture. Maybe I'll just do it over here. So if you know about it, you could actually draw the coordinate graph of this, if you know what it looks like. This is what the graph of s of x equals to x squared looks like. And by the horizontal line test there, it doesn't hit any negative things, so it's not onto. And by the horizontal line test there, it hits twice, it's not 1-to-1. Okay. Now if you restrict, if you don't consider the negative numbers, so if you just go from the real numbers to the positive real numbers, it's definitely onto, but it's still not 1-to-1. I'm just going to write this down because we're very short on time. So this one, is it 1-to-1? No, same problem. Is it onto? Yes. Is it bijective? No. And then what we do is we fix this problem. So the issue then becomes part of the graph, these negative bits. If you throw out those negative bits, the inputs, the graph looks like this. It's 1-to-1 and onto because it's increasing. Is it onto? We'll see that a bit. Maybe I'm going to do a second video here, so we'll have to slow down.